In this video, we're going to look at a special case called difference of squares. The first thing that I want you to note that this works for binomials, which means that the expression needs to have two terms. Also, it's super specific in that your binomials must have perfect squares, and those perfect squares, since this is called difference, need to be subtracted. Okay, so before we look at the factoring, let's look at why this works when we multiply. So if we have x plus 7 times x minus 7, and we use our area model to multiply or expand, we get x squared in our top left, negative 49 in our bottom right, 7x, and negative 7x. Once you combine everything, our 7x's cancel, and we're left with x squared minus 49. A binomial that's subtracted, perfect square, perfect square. So let's look at another one. 3x plus 4, 3x minus 4. We get 9x squared minus 16, 12x, negative 12x. Same idea. Our middle x terms cancel. We're left with 9x squared minus 16. So when we've identified a difference of squares situation, it factors into the square root, ends up being our first term of this end result first term. The other part of each binomial is the square root of the second term, and we have one positive, one negative. So following that pattern, the square root of x squared is x, square root of 144 is 12, one positive, one negative. It doesn't matter which one goes where. Next example, square root of 36x squared is 6x. So each term will start with a 6x. Square root of 100 is 10. One positive, one negative. Note that this isn't factored completely because we could actually pull a 2 out of each term. However, it's okay if you don't factor the coefficients all the way as long as the variables are factored all the way. So that one we'd call good. This one you might get stuck in that pattern, say 5x. 5x gives me 25x squared. 7 gives me 49. However, in order for our middle terms to cancel like these above, we had to have one of each sign. But that won't get me to a positive 49, and so if you run into the sum of two squares, it's actually not factorable. So our last three examples, we have a 2x and a 2x, a 1 and a 1, positive and a negative. So don't forget that 1 is a perfect square also. With this one here, we have a 3x squared, since that's next to the fourth, 3x squared, 4, 4, positive, negative. And then our last one, a lot of times students would factor this right away. It's a perfect square minus a perfect square, and that's fine. However, don't forget to identify your greatest common factor first. We can pull out a 4x squared, which leaves us with 4x to the fourth minus 9. Leave that 4x squared out front. Here we have another difference of squares case. We'd have a 2x and a 2x to get 4x to the fourth, a 3 and a 3, one positive, one negative to get that minus 9 there. And that is it.